time already? I guess it is. Welcome back to Café con Chemistry. Hopefully, you are also enjoying a cup of coffee as we delve further into kinetics. As we previously discussed, the rate is defined as a change in concentration over a period of time. We will begin to expand on this further. Our discussion today will cover the rate of reaction, calculating rate including average, instantaneous, and initial rate, and then lastly, expressing rate in terms of reactant and product concentration. When calculating the rate of a reaction in respect to the reactant, the following equation will be used. This is for a general reaction of the form of A to B. The equation states that rate is equal to the negative of the change in concentration over a period of time. The change in concentration is the final concentration, denoted as A subscript 2, minus the initial concentration, denoted as A subscript 1. This is all divided by the change in time, denoted in a similar manner. This can be condensed to negative delta A divided by delta T, where delta refers to change. Let's talk about the equation in a little bit more depth and how to use it. When running an experiment as a scientist, we measure the change of concentration for the reactants and products. As a reaction progresses, we expect for the reactant concentration to decrease, and as a result, the products increase. The negative sign in this equation is vital because the reaction rate must be positive. If we calculate the rate in respect to the reactant, A, the final concentration will be lower than its initial. In order for this equation to yield a positive answer, the negative sign is included. However, if we wanted to determine the rate of the reaction in respect to the products, the equation will be the same except we don't need the negative sign and the concentration is in respect to B. The equation reads, rate is equal to B divided by delta T. Remember, the final concentration of B is higher than its initial. Now that we have covered the basis of rates, we can expand further on it. As a reaction progresses, the rate varies. Let's take, for example, the following reversible reaction. Ethene gas plus ozone forms acetaldehyde and oxygen. In this equation, for every molecule of ethene that reacts, a molecule of ozone also reacts. We can write a general rate for the reaction which shows that ozone and ethene decrease at the same rate. This expression is as follows. Rate is equal to the negative of change in ethene divided by the change in time. This is also equal to the negative of change in ozone divided by the change in time. If we were to plot the following data for concentration versus time, we would get a curve. This means that the rate is changing over time, whereas a straight line would have indicated that the rate is constant over time. If we were to take the rate at varying points of this graph, we would observe that the rate decreases throughout. As ozone reacts, there are fewer molecules of ozone to collide with the ethene molecules, so the rate in respect to ozone decreases. When calculating rates, there are three types: average rate, instantaneous rate, and initial rate, where average rate is the rate over a finite period of time, which is the slope between 2 points. If we were to apply this concept to the previous graph, determine the average rate from 0 to 60 seconds, we would first have to write out the rate of the reaction and solve it. The rate of the reaction is as follows. Rate is equal to the negative of the change in ozone divided by the change in time. Now that we have the expression, let's plug in the appropriate values. This gives us a rate of positive 3.50 times 10 to the negative 7th mole per liter seconds. In this example, we calculate the average rate of the entire period. However, you can calculate the average of any period of time between 2 points. For instantaneous rate, this looks at specific time in the reaction, which differs from average rate, which looks over a given period of time. In order to calculate the instantaneous rate, you must first identify the time. In this example, we choose 35 seconds and determine the slope of the tangent line through the point 35 seconds. Initial rate is the instantaneous rate when reactants are first mixed together at T is equal to 0. The initial rate plays an important role in kinetics because it is used to derive rate laws, which we'll go into more detail at a later time. Up until now, we have written rate in respect to individual reactants or products. However, we can write a larger expression that relates both reactants and products into a single expression. Let's continue with the same reaction. As our starting materials, ethene and ozone, react, the concentration decreases, and our product concentrations increase. The rate of reaction would be as follows, which we defined earlier. This expression shows that as the concentrations of our reactants decrease, our product concentrations increase over time. When writing rate expressions in respect to reactants and products, we can consider the following general reaction. A reacts with B to form C and D. Each reactant and product have a coefficient that we must take into consideration in the final rate of the reaction. I know today's discussion covered a lot of information in respect to rate equations and calculating different types of rates. Thank you for watching and have a wonderful day.